Now one some other topics related to cache. Okay, so now there are some types of caches. Okay, we will look into types of caches. Okay? Types of caches. We will look into types of caches. Right now, see what is the directly I am giving. Okay, what is the write through cache? So what is the write through cache? What is the write back cache? Okay, maybe I think I have diagram. Yeah, see, look here, look here. Okay, you have, if something is right, okay, only see, only if, first of all, assume that write request come. Okay, write request come to the cache. Okay, write request come to the cache. Write request. Okay, write request. Write request. Now, whether you will get a hit or you will get a miss. Okay. Now, if you get a hit, then there are two types: write through cache and write back cache. Yes. Then there are two types. This is write allocate. This is write. So based on the write, okay, based on whether you will get a hit or miss, whether you will get a hit or miss, your cache will be divided into four types. Okay, your cache will be divided into four types. Write through cache, the name itself says write back, say write back, write allocate, and no write allocate. Okay, so it's used for write. Okay, it's used for write. Now now see, in a write through, what happens when CPU writes data? You update the cache. Okay, so it will be the hit. Okay, you will get a hit. So update the cache, immediately update the main memory. Okay, you update the cache, update the main memory, because you have to write something, right? And you got a hit. You got a hit, right? Yes or no? Yes or no? You got a hit, and it is a write through cache. Yeah. So always update in main memory write through. Yes. So you update the cache and main memory both. Okay, both update, both updates. Now, what is the write back cache? What is the write back cache? So it is also used in case of hit scenario, right? In case of hit scenario, as I already as I have told. So in the hit, you have write through and write back, right? So what is the write back says? What happens when CPU writes data? Update only cache. Okay, update the cache only. Update cache only. Update the main memory later. Okay, you update the main memory later. When you update, when the cache block is evicted, right? When the cache block is evicted. So when the cache block is evicted, right? When the cache block is replaced by some other cache, right? Is replaced, and you have written something. So you must have to update the main memory, right? Otherwise, you will get the different problems. Like, assume that in a bank account, you have updated 1,000, right? Example, you have updated 1,000, and then you have updated 1,000, but in the system it is showing 500. In the system it is showing 500. You have updated 1,000, and but in the system it is showing 500. So this is really a problem, right? This is really a problem. Just it's I have given analogy of bank. I have given analogy of bank. I hope you can get it. So here, when the cache block is evicted, at that time only you update the main memory. And now it uses a dirty bit, right? So dirty bit will says that it is modified, but not returned to main memory. Got it? Now you got the real case of dirty bit. Like dirty bit will say is that this bit is modified, and when it is evicted, right? When it is evicted, at that time you update the main memory, right? You update the main memory. Yes or no? Got it? So this is the right back. Okay, this is the right back. Its other name is right behind. Okay, right behind. Now, now what happens in case of right miss? Okay, what happens in case of right miss? So miss happens. So you have two types, right? Two types. First is right allocate and no right allocate. So we look both. So question is, what if a miss? Okay, question is what if a right miss occurs? What if a right miss occurs? So what is the policy? What is the right allocate policy? It says that bring the block into the cache, then add into the cache. So what is the flow? Write means happens, load blocks into the cache, and you write it. Okay, you write it. Got it? Got it? You bring the back. Okay. So what is the flow? What is the flow? In a write means you load the block into the cache, you load the block into the cache, and then you write it. Okay. So see here, it's bringing the data from main memory to cache, right? Bringing data from main memory to cache. Okay. So that's what here written. You bring the block into the cache and then you write it, and it works best with write back. Okay. It works best with write it. So write allocate plus write back. Okay, plus write back. Write allocate plus write back. Okay. Now, what is the another policy? Another policy is no write allocate or write non-allocate. So what if a write miss occurs? Okay, what if a write miss occurs? So you do not load the block into the cache. Okay, you write or you update. Okay, write or update directly to main memory. Okay, you update directly to main memory. So what is the flow? If the write miss happens, you directly write to the main memory. And why it works best with the write to? Okay, so no write allocate plus write through. Okay, so these are the combinations. Okay, and directly and non-directly pyqs are coming, like directly pyqs are coming, and that too in the recent years, if you look the pyqs directly from this topic, pyqs are coming. So this is again very much important. So for best performance, you can use this combination write through with no write allocate, and write back plus with write back with write allocate. Okay. So if someone can ask, sir, why this combination only? So see, no right allocates is you directly when miss happens, right? So one miss combination we have taken, one hit combination, right? So miss combination says directly right to the main memory. What the hit combination will say, you update both, right? You update both. See here, you update both, right? Both the updates. So that's why here in this case, everything is in sync, right? Everything is in sync, right? Is in sync. Everything is in sync. Like main memory is updated every time, right? Main memory is updated every time. Like main memory is in sync every time, right? Now now here also we have taken one miss combination. Okay, and we have taken one hit combination, right? So what the miss will say, you what the miss will say, you bring the block into the cache, right? You bring the block into the cache, and you update only here. Okay, you update only here. Okay, so that is what your write allocate says, right? That is what your write allocate says. See, bring the block into the cache and then write into the cache. But what the write back will say, write back also say similar thing. See, you update only cache, you don't update the main memory later. So here here like this combination. Okay, this combination is lazy. Okay, this combination is lazy to update the main memory, right? To update the main memory. Yes or no? So, uh, right? This combination is lazy to update the main memory. Okay. So this way you will get the best performance. Okay. This way you will get the best performance. Add through with no add allocate and add back with add allocate. Okay. Now the last topic is remaining in the case is local miss and global miss. Okay. But before that, let's say if someone can ask, sir, what happens in case of word miss? Okay. What happens in case of word miss? So what happens in case of word miss? Okay. So in the right we have divided into different types, but in case of word miss, you bring the block, you bring the block to cache. Okay, you first bring the, because it is miss, right? You bring the block to cache, and then give, and then cpu will access. Okay, and then cpu access again. Okay, cpu will access again. Got it? So in herd means they in for the case of herd. Okay, for the case of herd, there is no such types like like your caches won't be divided into different types. This is the general thing, right? This is the general thing which happens in case of miss, right? This is the general thing happens in case of miss, right? Happens in case of miss. Okay. So now we will see what is the local miss and what is the global miss. So local miss, this is also important. Like now we will see now I told you, like your PYQs so these of the thing I am discussing, of the thing I am discussing, and which is very important. So look here, what is the local miss? Local miss at this case divided by access to this case. Okay, access is to this case. So now what does it mean? Assume that uh, maybe yeah, assume that you have, if this is the cache, if this is the L1 and this is the L2. Okay, now what is the meaning? What is it the local meaning? It considers only one level. Okay, only considers only one cache level. Okay, and ignores what happens elsewhere. Okay, you ignore what happens everywhere. You only consider only one level. So, for example, see, example, if it is L1 cache, okay, L1 cache, if it is accessed 1000 times, okay, if it is accessed 1000 times, right? Now, if this is your CPU, right? If this is accessed 1000 times, maybe I can give this way, okay? If this is accessed 1000 times, okay, 1000 times, and 100 times there is miss, okay, there is miss. So what will be local misset? What will be local misset of L1? So local misset of L1 will be 100 divided by 1000, right? 100 divided by 1000. So that's only written here. So that's why you have to look into locally, okay? You have to look into locally misset, locally misset. Now, same thing, okay? So 100 times you will get a miss, 100 times you will get a miss. So 100 times you go to L2, 100 times you go to L2. Now assume that, let's say 10 times miss happens, okay? 10 times miss happens. Now, what is the local miss rate for L2? Okay, local miss rate for L2. So 10 misses to 10 misses divided by how many times you access. You have accessed L2 100 times, right? So 10 divided by 100 into 100%, right? So this way you have to give local and global miss rate. Okay, this way you have to give local miss rate. Okay, this way you have to give local miss rate. Now I will explain what is global miss rate. So what is global misset? Global misset means misses in this case divided by total efficiency, total memory efficiencies by CPU. Okay. So what is meaning? Relative to all CPU accesses. Okay. Relative to all CPU accesses. So so see. Okay. So see this. If this is the same scenario. Okay. Same scenario. So what is the global miss for L1 and what is the global miss for L2. So what is the global miss for L1 and what is the global miss for L2? So L1, how many misses L1 have happened? 100. Okay, 100. And now you have to check globally. Okay, you have to check globally. Like total references made by the CPU. Okay, so globally you have to check. So how many times CPU have reference? So 1000 times. Okay, 1000. So you have to put here 1000. Okay, you have to put here 1000 into 100. Right? Now, what is the global miss for L2? How many miss L2 happen? 10 misses, right? 10 misses. So 10 divided by, see, for the locally, what we are doing for the local misses, for the local L2 misses, what we are doing, we are saying that how many L2 accesses, okay, so that is 100. But in the global miss, okay, in case of global miss, we are seeing globally, okay, we look into global picture. So globally, CPU have requested 1000 times. So what we have to do? We have to put here 1000, okay? The denominator, we have to put 1000. Got it? So whatever is your answer, that will be your global L1 rate and global miss set for L1 and global miss set for L2. Okay? Yeah. So now just last topic. Okay, just last topic. Okay, so this is all about local miss set and global miss set. So this is the last topic in the cache. Okay. So all the data in L1 is guaranteed to be present in L2. Okay, inclusive means L1 is subset of L2. Okay, L1 is subset of L2. So every data in L1 is present in L2. L2 is a superset of L1. But effective cache capacity is reduced because of duplicate blocks, right? Because of the duplicate things, like it is present in L1 also, something is present in L1 also, something is present in L2 also. So that's why, like effectively, if you look, okay, if you look the effective cache capacity, then it will be reduced. Okay, then it will be reduced. Then it will be reduced. Now, what is the exclusive cache policy? What is the exclusive cache policy? It says that L1 subset of L2, sorry, L1 intersection of L2 will be 5. Okay, will be 5. So there should be no intersection. Okay, there should be no things which should be common. Okay, no things common. No things common. Okay. So no block is duplicated between L1 and L2. A block exists in either L1 or L2, but never both. Okay, never both. Either it is present in L1 or it is present in L2, but never both. Okay. So it gives the maximum effective cache, right? It gives the maximum effective cache capacity, like L1 and L2, right? Some things you will put into L1 also, and if L1 is full, you can put into L2 also, right? So you will get L1 plus L2, which is usable. Yes. Now, what is the last policy? So last policy is non-inclusive cache policy. Okay, so L1 is not a superset of L2. Okay, so no strict requirement that L1 blocks must exist in L2. So there is no strict requirement that L1 block must exist in L2. So it provides the better effective cache size, like less duplication of data. Okay, less duplication of data. And if you look into your processor, okay, see, if you look into your processor, many processor uses this. Many processor uses this. Okay. Some of the processor still uses exclusive, but many processor uses non-inclusive. Okay. And none of the processor in your latest processor uses this. Okay. This is not used. This is not used. Now, got it? So yeah, so this non-inclusive case policy, there is no strict requirement. Like something is present, something is not present, something may present, not present. Like there is no such requirement. Okay, it may present or it may not present. Okay, it may present or it may not present. There is no such things. Okay, that anywhere things can be present. Okay, anywhere things can be present. Yeah. So with that in the anti-cache notes, okay, anti-cache, some very important things I have put. Okay, I have put, okay, very important things I have put. Very important things I have put. So we are discussing about the pipelining. So I'm saying that it is the most important topic after cache organization. Okay, and every year gate PYQs is coming. So I'm giving one real analogy, that why pipelining is useful. So assume that you currently don't have pipeline, right? You currently don't have pipeline, and all this washer, dryer, and folder, you have three machine, and each machine is taking one unit of time. Okay, one unit of time. Okay, uh, one unit of time. Okay, one unit of time for clothes. So if I have 10 clothes, so how much time it will take? So my one cloth will go. Okay, one cloth will go, and one unit and one unit. So total three units. Okay, because this is the entire machine, right? This is the entire machine. So this is the entire machine. So for 10 clothes, how much time it will take? So for one cloth, it is taking 3 unit of time. So for 10 clothes, it is taking 30 units, right? 30 units of time. 30 units of time. Now, now this is the case for non-pipeline, right? This is the case for non-pipeline. But now, let's say we have pipeline. Okay, we have pipeline. So if we have pipeline, then all these three machine are single unit. Okay, single unit. This is one separate unit. This is separate unit. This is separate unit. Washer, dryer, and folder. So now how much time it will take? How much time it will take? So let's say one cloth is going, okay, one cloth is here currently in 1 unit, right? In this is 1 unit of time. So here one cloth is here, okay, one cloth is here. Now in the second unit of time, one cloth, the first cloth have already done in the washer, right? Then it will go to the dryer. So it will go to the dryer, right? But when it is working in the dryer, so your washer is free, your washer unit is free. Tell me, your washer unit is free? Yes. So you can put one another cloth here, you can put one another cloth here. Now in the third unit of time, okay, third unit of time, same thing. So this is the maybe I can add the C1, okay, C1, C2, C2, right? So new cloth have come. Now in third unit of time, this C1 is done with the dryer, so he go to the folder. Now C2 done with the washer, so he go to the dryer. And in the third unit, one new cloth have come, which is C3, right? C3. So you see here that in the pipelining, you are utilizing each and every machine very efficiently, right? Very efficiently. So if you do like this way, okay, if you do like this way, how much time it will take? So see, currently first cloth, okay, so C1 cloth have to execute each and every unit, right? Like one unit here, and one unit here. So for one cloth to coming out, okay, so for one cloth to coming out of each and every three machine, okay, for first C1 cloth to come out of three machine, how much time it will take? Three time, right? Three time plus how many clothes are remaining now? How many clothes are remaining now? So one cloth we already processed, right? One cloth we already processed. So nine clothes is remaining. So nine clothes. And now if you see from fourth cycle or fourth unit, okay, four unit of time or four cycle, you will see that on each cycle you will get one cloth, right? C2 you can get. Now in C5 you can get C3. And now on 6 you can get C4. Okay, it is done from all the units, right? So each of the nine cloth, the rest of the nine cloth will take one unit, right? Will take one unit. So 12 units of time, right? 9 plus 3 is 12 units. So you see here, if you don't have pipeline, then it taking 30 unit. But if we have pipeline, then it just take 12 units, right? It just take 12 units. So with this, you have seen that we are efficiently utilizing the resources, right? Efficiently utilizing the resources. So now if you can see the definition, so what it says, execution of multiple instruction, you have to execute multiple instruction which is overlapped in time and just like an assembly line, right? So you see here, this is like an assembly line, like one after another, right? One after another. So while one instruction is in execute, next is in decode, next is in fetch, right? So in your classical five-stage pipeline, this is the classical five-stage pipeline or risk pipeline, right? Risk pipeline. In that you have five stages, like instruction fetch, then instruction decode, then you have execute, then you have memory, and write back. So uh, these are the five stages of classical pipeline, right? So now here instruction fetch is fetching the instruction. Here instruction decode plus register read you can do, right? In the execute you can do execute with the help of ALU. now in now in the memory, if you want something in the memory, you can do it in the memory stage. And write back means writing back into the register, right? Writing back into register. So see, if you are executing multiple instruction, right? If you are executing multiple instruction, let's say I1, I2 and all, I1, I2, I3 and all, so on, right? So in the C1 cycle, okay, so if this is the cycle 1, so I1 will be here, right? I1 can execute here in the C1 cycle, like in the first cycle, yes. Now in the C2 next cycle, I1 is done with the instruction fetch, so he can go to instruction decode, and similarly new instruction can come because this stage is empty, so I2 will be done here. Now similarly in the C3 cycle, I1 is done with the decode stage, so he go to the next stage, which is execute, like step by step, right? Step by step, one after another, this instruction will go on. And I2 have done completing instruction fetch, so he will go to instruction decode, and new instruction I3 will come. Yes, new instruction I3 will come. So this way on each cycle, multiple instructions can execute in different stages, different stages. So we are better utilizing the resources, and we are saving the time also, right? We are saving the time also. So till now, it's everything. It's clear that why we are using the pipelining. Why we are using the pipelining? Yes. So why pipelining? So it improves the throughput, right? It improves throughput. Throughput means instruction per unit time. Like per unit of time, multiple instruction can be executed, right? Multiple instruction can be executed. You see here that in our non-pipeline case, we have to wait, right? We have to wait for all the units to execute, and then only we can proceed with the next cloth, right? Next cloth. But if you see in the pipelining, in each unit of time, in each cycle, multiple clothes can be executed parallelly, right? Multiple clothes can be executed parallelly. So if we apply the same thing in the pipeline, multiple instructions can execute parallelly, right? Multiple instruction can execute parallelly. So now this is the important point, that it improves the throughput, like instruction per unit time. Now next point is, it does not reduce single instruction latency, right? Single instruction latency. Why it doesn't improve? See, it does not reduce single instruction latency. Now if you care carefully, okay, now if you see carefully, if you see carefully, so if you look here, if we have this case, right, here also one cloth is taking, okay, one first cloth is taking 3 unit of time, right? 3 unit of time, like 1 unit for here, 1 unit for here, and 1 unit for of here. Let's say you have only one single instruction, right? So one instruction is using 1 unit, 1 unit, and 1 unit. So that is in total 3 unit. But now, similarly, in case of pipeline, if you have only one instruction, okay, one cloth or one instruction, okay, one cloth. So one cloth is taking how much time? So see, look into C1 cloth, okay, C1 cloth. So it is taking 3 unit, right? It is taking 3 unit. So you see that whether we use non-pipeline or whether we use pipeline, it doesn't matter. It doesn't matter, because both is taking the same time. So it is not improving the overall latency. Okay, it is not improving the overall latency. So it does not reduce the single instruction latency. Okay, single instruction latency. Now, now, now whatever we see, these all the things, right? These are the very important part. This is the very important, because these are the very important formulas. It comes again and again in the PYQs, and each and every gate questions. Each and every gate question, this is coming again and again. So now see this. This is the formula for pipeline total time for n instruction. Okay, pipeline total time for n instruction. See how we are writing it. How we are writing it. Yeah, I'm showing here. Okay. So let's say if you have k stages, okay, k stages. If you have k stages, okay, k stages, and you have n instruction, okay, and you have n instruction. So tell me how to find it, okay? And TP is pipeline cycle time, okay? It is cycle time. TP is pipeline cycle time. Now, now see, if you want to execute an instruction, okay, you want to execute an instruction. Now tell me, first instruction will take, so we have to find total time we have to find out, so first instruction, how much time it will take? First instruction, how much time it will take? It will take k stages. Yes, we have seen here also. See, here, our first instruction, like C1 cloth, is taking all the stages at 1, 2, and 3. So that's why we have wrote it separately 3, right? And then rest of the 9 cloths, okay, rest of these 9 cloths is taking one unit, right? One unit. Now, similarly in this case, first instruction will take how many cycles? So first instruction have to go to each and every stage, right? Each and every stage. So k cycles, right? K cycles for first instruction. Now plus, okay, plus rest of the, how many instructions are left? N minus 1, okay, n minus 1. So n minus 1, rest of the n minus 1 instruction will take one cycle. Yes or no? They will take one cycle, because after that, on each one cycle, you will get different instruction. So n minus 1, okay, rest of the instruction into one cycle, right? One cycle. So this is the total cycle, okay? This is the total cycles in case of pipeline, okay? In case of pipeline. Now into, if you multiply, this is the cycle, if you multiply cycle time, TP, okay? TP is the cycle time. You will get the total time, right? You will get the total time. So this is nothing, right? That's what only written here. K plus n minus 1 in like K plus n minus 1 cycles into TP, okay? Into TP. Now, now next important formula is speed up, okay? Speed up. So speed up formula is, so here it's speed up, this formula is speed up of pipeline over non-pipeline, okay? Over non-pipeline. Then only you can use this formula, okay? Then only you can use this formula. So whatever term is after, like whatever, whichever you have to find, okay? So you have to find speed up of pipeline, so that you have to write in numerator, okay? That you have to write in numerator, and other term you have to write in denominator, okay? Or I have, yeah. So whichever term you have to find, that you have to write in denominator, okay? Whichever term. So pipeline you have to write, so that you have to write denominator, and over non-pipeline. So here non-pipeline you have to write, okay? So please careful, because many PYQs are there in that you will take. Because let's say in exam they have in GATE 2027, in GATE 2027, let's say they are asking that speed up of non-pipeline over pipeline, okay? Speed up of non-pipeline. So if they ask a reverse thing, so non-pipeline term will come in denominator and pipeline term will come in numerator, okay? So whichever is asking, that you have to write in denominator. So please take care of this, please take care of this. So that's what we written here. This is the time for pipeline, and n into Tn. Okay, so Tn is the non-cycle, like non-pipeline cycle time. Tn is non-pipeline cycle time, and n is number of instruction. Right, n is number of instruction. So each instruction will take Tn time. Right, each n instruction will take Tn time. So n into Tn divided by k plus n minus 1 into Tp. Okay, so this is the speed up. Now this is the ideal speed up time. Ideal speed up time, in that what we are doing, it is an ideal speed up. So in the ideal speed up, see here, we are assuming that we are assuming that n to be infinite, right? N to be infinite. So if n is infinite, like we have so much instruction, okay? We have so much instruction to execute. Then what we do, we just divide, we just remove both the terms, like, right, n and n, because this term and this term is almost equal. So what we are left with Tn divided by Tp, right? We are left with Tn divided by Tp. So this is the formula for ideal speed up, okay? Ideal speed up. Now, yeah, so TP is given here, pipeline clock period cycle time, or time taken for one pipeline stage in pipeline execution. Okay, so this is the TP, like pipeline cycle time, and this is the TN, like time taken to execute one instruction without pipeline, okay, without pipeline. Now, now proceeding further. So now if you, let's say, what is the TP and TN in case of different stages, right? Different stages. So example, like, if these are the stages, right? These are the different stages. So example, it takes, and there is something called as register, right? So there is something called as intermediate buffer, right? Intermediate buffer. There is something called as, these are called as intermediate buffer, and that is used for storing the information, okay? Storing the necessary information or computation which is required for other stages, right? So that's why intermediate buffer is used. So it's like kind of a register only, okay? Buffer is kind of a register only. So here, how to find the TP? How to find the TP if each stages have different delays, right? Here, let's say 5 nanosecond, then 3 nanosecond, let's say 2 nanosecond, and let's say 1 nanosecond. And each intermediate buffer will take 1 nanosecond, okay? So what is the TP for it? TP formula you can find with maximum of segment delay plus register delay. So register delay is 1 nanosecond, right? And maximum of segment delay, so maximum of 5 comma 3 comma 2 comma 1, so that is 5, right? So in total it will take 6 nanosecond, okay? Total it will take 6 nanosecond. So someone is asking for synchronization. Yes, for synchronization, the this formula TP will be maximum of segment delay. Like it is taking 5 nanosecond, right? Because of it is the bottleneck in all the stages. It is the bottleneck in all the stages. That's why we are taking maximum. And how to find the TN, like non-pipeline cycle time? You have to just do sum of all segment delay. Okay, only segment delay. So that will be 5 plus 3 plus 2 plus 1. So that will be 8, 9, 10, and 11 nanosecond. Okay. So this way you have to find it. Okay. This way you have to find it. Now, now, next thing is important is throughput. So first of all, what is throughput? So throughput is number of instruction which is executed per second. Okay. Per second, number of instruction which is executed. Now see, uh, here if the latency of pipeline, yeah, so this is the TP and TN. So what is the throughput formula? Throughput formula is 1 divided by TP. Okay, 1 divided by TP. Directly you can find. Also also here we have to find throughput of pipeline. Okay, we have to find throughput of pipeline. So see, if you want to know how this have come, so maybe I am adding here. Okay, so let's say k plus n minus 1 time is into tp. Okay, into tp time is utilizing for n instruction. Okay, this much time is taking for n instruction. Okay, now we want per unit of time. Okay, per second, how much instruction to execute? So 1 second. Okay, how many instruction to execute? Yes. So what we do, this is n divided by k plus n minus 1 into tp. Okay, into tp. So this way also you can find. But now take n to be very large. Okay, take n to be infinity. So you can remove both the terms, numerator and denominator. So what you are left, 1 divided by tp. Okay, 1 divided by tp. So that's what it is written here, 1 divided by tp, right? Now everything is clear till now. Like we have seen different formulas, TPT and throughput and all. Now we will see about hazards. Okay, now we will see about hazards. Okay, so now first of all, what is the hazard? Okay, what is the pipeline hazard? So pipeline hazard means condition that prevents next instruction from executing in the next cycle. Okay, or conditions. Okay, conditions that create stalls. Okay, that create stalls. Those are called as stalls means extra cycles. Okay, stalls means extra cycles. So those are called as hazards, right? Those are called as pipeline hazards. Now, generally, we have three types. Okay, we have three types of hazard. So, structural hazard, data hazard, and control hazard. So, structural hazard, which means when two or more pipeline stages, they need the same hardware at the same time. Okay, like when two or more pipeline stages, they need the same hardware at the same time. Like we are here scarcity of resources. Okay, scarcity of resources. If you have scarcity of resources, then we can't perform like multiple instruction in a like if two or more stages need the same hardware, right? If two or more pipeline stages they need the same hardware, then we can't do at the same time. Because if two stages demand the same hardware, we can't do it. So that's why that's why you have scarcity of resource. Okay, that's why you have scarcity of resource. So that creates the extra cycle which is called as hazard. Okay, that's called as structural hazard. Now see, if I want to give explanation I can give, but yeah, so assume that you have instruction fetch, instruction decode, then you have execute, then you have memory. Okay, then you have write back. Okay, then you have write back. So what will happen if you keep on executing? Okay, let's say I1. Okay, so let's say in the cycle C1, so I1, or how I should. Yeah, I just want to explain like this way. So let's say I1. Okay, now in the C2, I1 will be here, I2. Okay, now in the C3, I1 is here, I2 and I3. Okay, now in the C4, I1 is here, I2 is here, I3 is here, I4 is here. Okay. Now if you look carefully, here two stages. This is the memory stage, this is the instruction fetch. Okay. Instruction fetch and memory both happens in the memory, right? Because we are fetching the instruction also from memory, and from the like instruction fetch. So we have to fetch the instruction from the memory, and this is the memory, like this is the data memory. Yeah, data memory, like we are if you want to, execute some data, you can go to the memory, right? If you want some data. Now if you see clear in the C4 cycle, okay, C4 cycle, let's say your one memory, okay, your main memory have same thing. Okay, have same thing, like it has instruction memory also, and it has data memory also. Okay, data memory also. Now what happens in the C4 cycle? Both these I4 and I1, both these stages will require this same hardware. Okay, this same memory at the same time. At the same time, both requires the same memory. Yes or no? So here, that's why it will cause the delay. Okay, that's why it is called the delay. That's why it causes the delay, and that's why the structural hazard happens. Okay, structural hazard happens. Now, if you are asking, sir, then how we have to do, how we can proceed. So in the real world, okay, in your classical five-stage pipeline, okay, classical five-stage pipeline, classical five-stage, you have two different memory. Like you have instruction memory also, which is only used for instruction, and data memory. Okay, so both are two separate memories. Both are two separate memories. Okay, both are two separate memories. Both are two separate memories. So what can happen, like instruction fetch can use this instruction memory, and this is used for data memory, so that is using data memory. Okay. So this way that can be solved. Okay, that can be solved. So there are many ways, like you can increase the hardware, resources and all. But it just for your explanation, I have told you. Okay. Yeah, so there is one question. So memory can be enabled for either C1 or C2, right? Yeah, memory, you can enable this memory. Like if you have single memory for both instruction and data, you can enable it. But see, in a pipeline, what we want everything execute happens in parallel, right? So if you execute either C1 or C2, what C1 or C2? I think I1 and I4. Okay, if you execute, I think I1 or I4. Okay, then you have to wait for some time, right? One instruction have to wait. Have to wait. So that's why it is creating stall. That's why it is creating stall. Got it? Yes. Okay. So now next type of hazard is data hazards. Okay. So what is data hazard? It occurs when instruction depends on the result of previous instruction. Okay. When some particular instruction depends on a result of previous instruction, then data dependency will be there, and data hazards you will get. Okay. Hazards you will get. And control hazards you will get, it occurs due to branch instruction. Okay. They occurs due to branch instruction. Now we will see this, that there are three type of data dependencies. Okay, there are three type of data dependency. First is row, which is read after write. It's also called as true dependency. The next is WAR. Okay, WAR. What does it mean? It means right after read. Okay, it's already written. Right after read, and it is also called as anti-dependency. And next is WAW, which is right after write, and that is also called as output dependency. Now, both these WAI and WAW are also called false dependencies, right? False dependencies. Why? Because they can be eliminated. Okay, they can be eliminated. They can be eliminated with the help of register renaming, right? Register renaming. Yeah, so I have already written both WAW and WAR dependency can be eliminated by register renaming technique. Okay, register renaming technique. Now, see this. Only row dependencies create row hazards. Okay, only row dependency create row hazards. WAW and WAI won't create any hazard. Okay, won't create any hazard. They both WAW and WAI won't create hazard. Only this row dependency create hazards. Okay, only this row dependency create hazards. So whenever there is a question that which dependency will create hazards, and So what you have to do, you have to only analyze and only analyze your dependencies. Okay, only analyze your dependencies. Now, maybe I can give one example here. Okay, so let's say example. Okay, example. R1 is the R2 plus R3. Then let's say R2, R3 plus R4. Let's say R3. Okay, let's say R2 again, R2 again, and R1, and then R1 plus R5. Okay, if these are the instruction, tell me row dependencies, row dependency WAW and WAR. You have to tell me all these dependencies. Which are the how many are the dependencies and which are them? Okay, which are them? Yeah. So see this. In the row dependencies, what is row dependency? Which is read after write. Okay, read after write. So read after write means we are reading something after writing it, right? We are reading something after writing it. So in the row dependencies, we are saying like this way, right? We are saying like this way. Okay. So see this I1 and R1, there is a dependencies, right? There are dependencies between instruction. So if this is the I1 instruction, I2 and I3. So there is I1 and I3 dependency. Okay. Now WAW, which means right after write. So see here, it is writing R2 and also it is writing R2. So which means these are the dependent, right? I2 and I3. It is right after write, right? Right, you are writing after writing. Now, what is WAR? WAR means you are writing after reading it. Okay, you are writing after reading it. So see here, if you look R2, okay, if you look R2, so you are writing here after reading it. Okay, so this is dependency. This is dependency. Now someone can ask, sir, this is also R2. Okay, this is also R2. Sir, this can be dependency? Can't this will be dependency? So no. Okay, so no. So no. Okay, only only there is dependency between I1 and I2. Okay, there is dependency between I1 and I2. Yeah, why we are not taking this as dependency WAR? So for each and everyone, okay, for each dependencies, see, for each dependency you have to remember that no dependency, if you are okay. So first of all these dependencies, okay, maybe I'm adding one point, that dependencies happens between instructions only. Okay, between instructions only. Okay, so example, let's say one another example if I want to give. Okay, one another example if I want to give. Let's say one another example. Let's say I1 is R2 plus R3, and then you have I1 plus I1, and you have R4. Okay, tell me how many row dependencies. How many row dependencies? So if someone can tell, okay, here it is I1. If someone is giving answer to, okay, so if this is also dependent, this is also dependent, so that is wrong. Okay, that is wrong. Only one dependency. Okay, only one dependency. So that's why I wrote here like dependency happen between instructions only. Okay, between instructions, those are dependency. Okay, between instructions, there are dependency. Okay, between instructions, there are dependency. And and see, why we are not taking this dependency. So if we are taking this dependency, okay, if we are taking this dependency, no dependency should come in between. Okay, no WAR dependency should come in between. So you have to please take care this, that whenever you are calculating any dependency, okay, let's say you are calculating your dependency, okay, between I1 and, let's say, one another instruction. Okay, let's say I1 and I5. Okay, so if you are calculating row dependency, in between no dependency should come. Okay, in between no row dependency should come. In between no row dependency should come. Okay, so please take care this also. So yes, okay, yeah. Now These are some important points regarding to dependencies. Okay, these are some important points regarding to dependencies. Now for O, okay, now for O dependencies. Okay, so here it's clearly written that only row dependencies will create the hazards. So how to find the hazards? So you have to execute normal pipeline. Okay, maybe I have written here or not. I'm not sure. I have written that point or not. Okay, yeah. So I have written here for checking the hazard. Okay, for checking the hazard, what you have to do? You have to do pipeline execution, and check if problem is present or not. Okay, you have to check if problem is present or not. Problem is present or not. So in your, so there is one question in your second example. I1 is not row. Nah, sir. I1 is row dependency only, right? I1 is row dependency only. Like not two dependencies, but one dependency, only one dependency between I1 and I2 instruction. Okay. So if this is the I1 and this is I2, so there is I1 and I2 instruction. So there is only one dependency. Like someone can tell so that there is two I1, right? Here two I1, so two dependency, but no, only one. Okay. So that's what I written here. That dependency happens between instructions only. Between instruction only. Okay. So now there are different methods. Okay, so here maybe I have wrote here like different data hazard solution. Okay, like if you have data hazards, right? These are the data hazards, like data dependencies. So it creates the data hazards. So there are two solutions. First is stall or bubble or delay solution. Second is forwarding solution. Okay, second is forwarding solution. Now, what is the stall solution? What is the stall solution? So stall solution is not making mistake solution. Okay, we are not making the mistake. Okay, in this solution, what we are doing, we are not making the mistake only. We are not making the mistake. So there are two ways. Like one is hardware way, one is software way. Hardware solution is that is delay. Okay, that is delay. Like we introduce the delay. Okay, we introduce the delay, and we only consider correct value. Okay, we only considers correct value, right? Correct value. Only considers correct value. And second is software solution, which means inserting no operation. Okay, NOP means no operation instruction, and that can be done by compiler. So it is instruction to give. Okay, like if this is the NOP. What is NOP? NOP means no operation. It won't doing anything. Okay, it won't do anything, and it is the instruction only to give the delay. Okay, to give the delay, and that can be inserted by compiler. That can be inserted by your compiler. Okay, like when you do GCC some code. Okay, GCC, like let's say example.c. Okay, so when you do compile, at that time your compiler will add no operation instruction. Okay, if he find there is a stalls or something. Okay, so that's why first solution is delay or stall solution. Okay, delay or stall solution. Now next is second solution is forwarding solution. So what is forwarding solution? Like open forwarding. Okay, open forwarding. So that is the hardware solution for data dependency by provided by compiler. So that is the hardware solution only. I think it's not provided by compiler. Okay, I think maybe it is. Yeah, it is the hardware solution only for data dependency. Okay, that's a hardware solution for data dependency. Like example, let's say if this is your execute stage. Okay, if this is the execute stage, and let's say this is also the execute stage. Okay, this is also the execute stage. So for what here we are doing, instead of waiting, whenever we are getting one result. Okay, whenever we are getting result after, because see, execute stage is done by ALU, right? Execute stage is done by ALU. So when ALU will generate some result, what we are doing, as soon as we get the result, we forward to the next stage. Okay, we forward it to the next stage. Like, because see here, like here things are dependent, right? I1 is like this I1 is dependent on this I1 to execute, yes or no? Like instruction I3 is dependent on instruction I1 to execute. So what we are doing, as soon as R2 plus R3 will be executed, see here, as soon as R2 plus R3 will be executed, R2 plus R3 will be executed. in whichever stage. So now in this I3, okay, we have to perform I1 plus I5. So what we are doing, we directly whichever result we are getting, we directly forward to the next stage, okay, forward to the next stage. And then the perform like computation will be proceed, okay, computation will be proceed. Tell me, do you have any doubt in open forwarding? Do you have any doubt in open forwarding? Right, so this is the open forwarding, like hardware solution for data dependency. Right, as soon as we get something, so we are transferring it to the next stage. So mainly it is execute to execute state, but it will be mentioned in the question, okay, it will be mentioned in the question, like which to which stage forwarding is happening, okay, forwarding is happening. Now now Now, one important formula here will be, these two are important. Like, see, many PYQs are there in which what we are doing, we are first finding CPI average, okay, CPI average. In many gate PYQs, okay, in many gate PYQs, these are the things happen, like CPI average. Like what we are doing. So because of the stalls, okay, so your ideal CPI is one, ideal CPI is one. But because of stalls, what we are doing, so we are getting extra cycles, right, we are getting extra cycles. So CPI average, okay, CPI average will be 1 plus 1 plus, like, stall frequency into stall cycle, okay. So you can use this formula to execute, okay. 1 plus extra cycles, okay, 1 plus extra cycles. And now, what is the one instruction execution time? What is one instruction execution time in average? So if you get CPI average, right? If you get CPI average for one instruction, you can multiply with the cycle time. You can multiply with the cycle time, right? It's like cycle into cycle time, right? Cycle into cycle time. So CPI means cycle per instruction, right? What is the CPI? CPI means cycles per instruction, okay, per instruction, how many cycles are, how many cycles are taking, right? So CPI into cycle time, CPI into cycle time. Now now next, now we look into control hazard, okay. So this is important for formula, like stalls because of the branch. Like if after the ith stage the condition is evaluated, if after the ith stage condition is evaluated, how many stalls you will get? I minus 1, right? I minus 1. Now, what are the different solutions for control hazard? What are the different solutions for control hazard? So there are four solutions. So solution one is stop fetching after every branch instruction, okay, until the target is known. Like, we stop fetching after every branch instruction till the target is known, okay, till the target is known. Now, next solution is static branch prediction, okay. So here we are predicting whether it is taken or not, right? Whether it is taken or not, taken or not taken, and based on that we are introducing extra delays, right? Extra delays. Now, next solution is dynamic branch prediction. So it's like IO. In if you come in your IITs and NIT, you will see there is something called as target buffers and all, okay, target buffers and all. What it is doing, there are many different things, BTB and all, okay, BTB and all, like different hardware. So what this technique is doing, this technique will speculate, right? This technique will predict that, let's say, you are you like this technique will see the previous sequence. Like how? So see, if your code is doing taken, if your branch is taken, okay, and let's say non taken but taken, so this technique will see that what the sequence it is following, and then it will predict. So it will predict that for this branch also it will taken, okay, this branch also it will taken. Now let's say if some sequence will take not taken, let's say taken, not taken, okay, then what it will predict not taken, okay, it will predict not taken. So that's why it is dynamic, okay, that's why it is dynamic. And the last solution is delayed branch, okay, delayed branch. So what here we are doing, we are we are putting delay slot, right? We are introducing delay slot here. We are introducing delay slot. And in the delay slot, what we are doing in the delay slot, whichever independent instruction we put, okay? So compiler puts independent instruction, okay, independent instruction in delay slot, okay, in delay slot. So this everything will be discussed, I think, if whichever course you would have taken in the in the computer architecture, right? Whenever you are learning the subject, but this is just required for the short notes, okay? These are the important points which are required for pipelining topic, okay? Pipelining topic and for the short notes, okay? For the short notes. So with that, I think pipelining topic is over, okay? With that, pipelining topic is over. Now we will see the last topic, which is CPU and control unit. Okay, CPU and control unit. Now, now, see, these are the important formulas. These are the important formulas. Okay. So first of all, what is the cycle time? So this you know, right? The time will be 1 divided by frequency. 1 divided by frequency. So same thing written here. Cycle time is 1 divided by clock rate. One instruction execution time. There, this we have already seen, that CPI, which means cycle per instructions, right? Cycle per instruction into cycle time, that will be your one instruction execution time. But now if you execute program execution time, so if you have n instruction, so n into CPI into cycle time, yes or no? One instruction will take this much cycle, so n instruction will take n into this much, right? N into this much, right? So this is the program execution time, right? This is the program execution time. Now what is MIPS? Okay, what is MIPS? So MIPS is million instructions per second. Okay, million instructions per second. So this you have to just take. I think they are not PYQs, but you can consider this from the definition itself, from the full form itself. It is clear that per instruction, million instruction is executing. Now, next point is two CPU having same instruction set can have different CPI and clock rate. Okay. Now, if you have two CPU, so they may have different CPI also, and they may have different clock rate also, right? It based on how your like how the system designer or how the architecture have made, okay, how the architecture have made it. So this is all about it. Now we'll see control unit. Okay. Now we'll see the next topic, which is control unit. So see, what is the job of control unit? Job of control unit is it directs fetch, decode, and execute cycle. So it will give the direction. Okay, it will give the direction at how to do fetch, decode, and execute cycle, and it generates the control signal. See, it generates the control signal for different units. Right? Its main job is to generate. It main job is to generate the control signal, right? Control signal for different units. Okay, different units. Like you have ALU, you have memory, you have IO, and different units. Like that. So its main job is to generate the control signal. Control signal. Okay. So it decides the sequence of micro operation, right? It decides the sequence of micro operation, like which micro operation will be. So you know, right, that one instruction. Okay, one instruction. Assume that you have to execute add I1 plus R2. Okay, add I1 plus R2. Add I1 plus R2. Now, if this is the one instruction, okay, this is the one instruction. Here, many micro instruction. Okay, many micro instruction, micro operation, or micro instructions are present, yes or no? Micro instructions are present. So in I think in the first in the prerequisite only, I have written here. See, what is the micro operation? So it is the smallest operation which CPU can execute in single step. Okay, in single step, so it is the smallest operation which CPU can execute, and the time taken to execute one micro operation is called as CPU cycle time, right? CPU cycle time. So that is the smallest operation which CPU can execute, okay? That CPU can execute. Now, your one instruction can have many micro operations, right? Many micro operations. So currently we are not saying this add I1 comma I2, okay, because here in short notes that is not required, okay? In the short notes that is not required. Otherwise we can see that we which micro operations it required. I think it's fetch. First you have to fetch it, then you have to decode it, okay? Then you just have to execute it and stuff like that. So those are the micro operations it will require, okay? Now, now now what the control unit will do, it decides that which micro operation it have to execute, like step by step, like first this, then this, then this, and so on, okay, and so on. now Now, there are two types of control unit. There are two types of control unit. First is hardwired. So, what is hardwired? What is hardwired? It control signals are generated using logic gates. Okay, using logic gates, control signals are generated, and and because of logic gates, those are faster, and it is difficult to modify. Okay, it is difficult to modify. Why? Because here see, once we here it is generated using logic gates, right? It is generated using logic gates, so your hardware is fixed, right? Your hardware is fixed. Now it is difficult to modify because you have to change many different logic gates, right? You have to change many logic gates and so on. So it's difficult to modify. It's difficult to modify. And what is the next type? What is the next type? Next type is micro program control unit. So so the control signal stored as micro instructions, okay, and executed by control memory, okay, executed by control memory, which is also called as ROM, and it is easy to modify and slower than hardwired, okay, it is slower than hardwired. So see this carefully, see this carefully. So what happens, there is something called as control memory, okay, there is something called as control memory in control memory, okay, there is something called as control memory, okay, and in the control memory what happens, different micro programs is stored, okay. So if this is the micro program, okay, micro program, and what the micro program consists of, different micro operations, right? Micro operations like micro operation 1, micro ops 2, okay, micro operations 3. Yes or no? Yes or no? Yes or no? Different micro operations it will version, because it is micro program, right? It is micro program. It is micro program. So micro program will have different micro operations, different micro operations to execute. So see this. Now in the control memory, these entire steps will be put, okay, these entire steps will be put, like different sequence it will put, okay, different, like if this is the micro program 1, so all the steps will be put here. This is the micro program 2, so all these micro operation steps are put on in the control memory. So now it will do, what the control unit will do, if let's say if you want to execute this micro program 1, okay, so it will execute, it will come to this, it will come to control memory, and it will execute step by step, okay, it will execute step by step, like it will execute the signal step by step. Yes or no? Did you got the micro program? Yes. Like like control unit, what it will do, like control unit what it will do, if you execute micro program 1, then it comes to micro program 1, and then it sends the signal, it generates the control signal. It because every control signal is already generated, because here we are storing in the control memory, right? We are storing in the control memory. So in each cycle all this will be given, okay, all this step by step it is given, all this step by step it is given. Yes. Right. So now uh, so this is the micro instruction, okay. What is micro instruction? One word in control memory, okay, one word in control memory, and it contains the control signal for one clock cycle, right? It contains the control signal. This is the micro instruction, okay, this is the micro instruction. Now what is the micro program? Program contains the sequence of micro instructions, right? Because see, one program have many instructions, so micro program have sequence of micro instructions, right? So this is simple, this is just a micro instruction, and this is the definition for micro program. right? Now we will see types of microprogramming. Okay, we will see types of microprogramming. So we will see types of microprogramming. So there are two types. First is horizontal microprogramming, and vertical microprogramming. Okay, vertical microprogramming. So here it is wide control mode. Okay, wide control mode. Why? Because here one bit for each control signal, right? If you have 52 control signals, okay, 52 control signals, okay, 52 signals, then here in horizontal 52 bits are required. Okay, 52 bits are required. 52 bits are required. Right? So here no decoding is needed. No decoding is needed. Why no decoding? Because here we are storing 52 bits for each of the signals, right? 52 bits for each signals, and it is fast also. It is fast also. But there is trade-off. That what is the trade-off? Trade-off is that the larger control memory, right? Large control memory. Why? Because we have to store for each 52 signals, right? For each 52 signal, 52 bits are required. So it is wide, right? It is wide control word. Wide control word. Now, what happens in case of vertical? What happens in case of vertical microprogram? So what we are doing, encoded control signals, right? Control signals are encoded. Control signals are encoded. So example, similarly, if you have 52, okay, if this is the 52, what you are doing, you are taking log base to 52 seal value, okay, 62. So what is the answer? I think it's 6, right? 6. So only 6 bits required. Only 6 bits required. 6 bits required in this case, because here decoding happens. Right here it is encoded. Here control signals are encoded. Here control signals are encoded. Right. So here, so see, look here. Here 52 bits are required, and here 6 bits are required. Okay. So as we are doing encoding, so here it requires the decoding. Yes or no? It requires the decoding. It requires the decoding. So here signals are grouped, right? Signals are grouped, and it is compact and it is slow. Why it is slow? Because decoding required. Okay. Okay. So both the methods have their own trade-off. Okay, both the horizontal and micro program have their own trade-off. Okay. Now, if you see the speed comparison, then hardwired is the fastest, right? Hardwired is the fastest. Now, this is the microprogramming. This is the microprogramming, right? Hardwired and microprogramming. And microprogramming have two types, like horizontal and vertical. So which is fastest? Which is fastest? Horizontal is fastest and then vertical. Okay, horizontal is fastest and then vertical. Got it till now? Got it till now? Yeah, and this is the control memory. So it stores. So control memory, it's usually ROM, okay, and it stores the microprogram. Okay, it stores microprogram. So I think this all about control unit. Okay, this is all about control unit. Got it till now? Till now, everything you got? Okay. Yeah. So one thing we have missed here, I think I forgot in the notes. Okay. See, like in the microprogram, there is a one fixed, like there is one particular format. Okay, one particular format. So what is the format? Format is, here you are storing control signals. Okay, control signals. Then you have mux. Okay, then you have mux, and then you have, I think, next address, right? Next address. So this is the format you have, right? This is the format you have. Mux, control word, and next address. I think it's this way, right? This way. So control signals will be stored here. Control signals will be stored here. Control signals will be stored here, and there will be mux for it. There is a mux for it, and next address will tell. Next address will tell that which to execute. Okay. So this is one control word. Okay. This is one control word. This is the one control word format. Okay. One control word format. One control word format. Right. So please add this also in your short notes. Okay. Add this in your short notes. Right. Now the last topic which is remaining is, we just have to see about DMA and interrupts and all. Okay, DMA and interrupts and all. DMA interrupts and all. So see, uh, yeah. So first is DMA. Okay, DMA. In the DMA, there are three methods. Okay, in the DMA, like like you do the IO. Okay, for IO. Okay, for IO. Now this topic is for IO. Okay, so for IO, there are three methods. Okay, there are three methods to do the IO. Okay, first is programmed IO, next is interrupt driven IO, and the last is DMA. Okay, DMA means direct memory access. Okay, direct memory access. Now see the definitions. Okay, once you look the definitions, like everything will be clear. Okay, and these are the important for the short notes, because if you want to see the entire course. Okay, entire course, you can come to the you can join the APT and you can follow my lectures. Okay, I have explained each and everything in a very much detail. Okay, very much detail. So please see the entire course and then only come to the short notes. Okay. So this is the programmed IO. This is the programmed IO. First method is polling. Okay. First method is polling. So what happens? What happens here? CPU. Okay. So let's say if this is your CPU, and these are the IO device. Okay, IO device. So what happens? CPU continuously check the device status. Like CPU continuously checks whether this IO is ready, whether this IO is ready, whether this IO is ready, and so on. Okay. And then CPU continuously checks the device status. And what happens? So what? How much total time it take? Total time is time to check the status, right? Like CPU will keeps on checking, keeps on checking, keeps on checking. So that's why it is also called as polling. So you polls it. Okay, you polls it. You CPU asks every yeah, do they want to send data or not? Yeah, do they want to send data or not? Do they want to send data or not? So it keeps on check the divide. It keeps on checking. So time will be checking. Time will be checking. Plus once it is ready. Okay, once it is ready, once this IO is ready. Okay, once this IO is ready, it have to transfer the data. So plus data transfer, right? Plus data transfer. So this is the time for checking the status and data transfer. So this is the total time required in case of programmed IO. Okay, in case of programmed IO. Now see here, CPU remains busy here. Like CPU is wasting the cycle, right? CPU is wasting. Why CPU is wasting? Because CPU is keeps on checking it, whether you are ready, whether you are ready or not, whether you are ready or not, and so on, right? So it is wasting the cycle. So it is simple hardware. It is simple hardware, but it is least efficient, right? It is least efficient. So here comes to solve this problem. Here comes the next method, which is interrupt driven IO. Okay, interrupt driven. So what here happens? Device interrupts. Okay, device will interrupts the CPU when ready. Okay, device will interrupts the CPU when it is ready. So CPU don't have to poll. CPU don't have to poll, like whether you are ready or not, whether you are ready or not, and so on. Like whenever the device will be ready, they will directly tell with the help of interrupt. Okay, they will give the interrupt, and they will tell the CPU that, hey CPU, I am ready. Hey CPU, I am ready. Okay. Now what is the total time? What is the total time taken? Total time taken will be interrupt overhead plus time to service the interrupt. Okay, time to service the interrupt. Yeah. So it is better than polling. It is better than polling, but still CPU involved in every transfer. Right? CPU is involved in every transfer. So here, what is this interrupt overhead time? Interrupt overhead time includes context saving, ISR. ISR means interrupt service execution, context restoring, right? So if you know how interrupts are executed, okay, maybe you have done in your operating system course, but let me write here high level steps. So what happens when interrupt comes? Okay, interrupt comes. So what happens? Interrupt comes, then you saves the context. Okay, you saves the context. So in the context, what you save different register, like PC, right? Like PC, then different flag registers, and so on. Okay, different things you are storing. Save the context into stack. Okay, into stack you are storing the context. Okay. Then before that, before storing the context, okay, maybe, yeah, before storing the context, what you do, you execute the ongoing, you execute current instruction, and then you do, okay, you execute current instruction, okay, you execute current instruction, and then you saves the context into stack, okay, then you saves the context into stack. Then what happens, when as soon as you got the interp, right, you saves the context, now you have to service it, right, because interp comes, right, interp comes, then you have to execute it, you have to execute it. So ISR means interp service routine, okay, interp service routine. So what is it is what it is, it is just a function, right, it is just a function. I hope you have seen the driver and all, like if you plug, so see, currently I'm using the tablet, okay, currently I'm using the tablet. So I have to, whenever I have used for the first time, so I have installed the driver for it, okay, I have installed the driver for it. So in the driver, this code is written, like interp service code is written, right, so that you have to execute ISR execution. Okay, and here also many steps have been there, we are not discussing in that much detail. You have to go to table, then you fetch the code, right, because each interp have different code, which is given. Then you have to go to that table, you have to check the function and so on, okay. But you can just imagine that interp service will be executed, and then once the interp will be executed, you have to restore the context, right, you have to, because you have to resume the instructions. So you restore context, you restores the context, and then once you restores the context from the stack, you resumes instructions, okay, you resumes your execution, you resume the execution, okay. So these are the steps, okay, these are the steps for interp, okay. These are the high level step, these are the high level steps, okay? These are the high level step, very high level step. I have not gone into that much detail because that is not required also, that is not required also. You just have to take this time, so interp overhead time plus time to service the interp, okay. Now, the last method is DMA, okay? Because see, here also CPU have to involved in every transfer, okay? CPU have to involved in every transfer. So that's why we are introducing new method, which is DMA, okay? Which is DMA. So what is DMA? DMA is direct memory access, okay? DMA is direct memory access. So what happens? It is used for high speed bulk data transfer. CPU will send two information to DMA. Okay, see what the CPU will do. CPU won't do this transfer and all. Okay, CPU won't do transfer and all now. CPU will give two information to DMA. CPU will give two information to DMA, like starting memory address and data count. Okay, data count. Like CPU will give the starting address and CPU will give the data count. Then what the DMA controller will do? DMA controller will go to this memory address, like starting memory address. It will go, starting memory address. It will go, and it will perform the data transfer. Right? It will perform the data transfer. Yeah, CPU just give the access of the buses, right? CPU just give the access of the buses. So DMA controller, they generates the address, they sends the control signal to memory, like it sends the control signal to memory, and now here DMA will do the data transfer. Okay, data transfer DMA will do. Now CPU is free. CPU is free during the transfer. Okay, CPU is free during the transfer, except the bus contention. Okay, except the bus contention. Now what happens? See, whenever DMA have to transfer something, right? Whenever DMA have to transfer, so DMA will, at that time only DMA will take the bus. Okay, DMA will take the bus at that time only. So at that particular time only CPU is free. Okay, CPU is free. Okay, because at that much time only CPU won't do anything. Okay, CPU won't do anything. Got it? So this is all about these three methods, okay, like program dio, interrupt driven, and DMA, okay, and DMA. Now now DMA also have three modes, okay. DMA also have three modes, right? DMA also have three modes. What are the three modes? What are the three modes? See here, why the DMA have three modes, why the DMA have three modes. So this is the transfer mode of how, cycles, like how buses will be taken. Okay, how buses will be taken. So based on that, you have three modes. First is burst mode, next is cycle stealing mode, okay, and the last is interleaving mode. Okay, last is interleaving mode. Now here in the burst mode, what happens? DMA controller, okay, DMA controller, it takes the control of the buses for entire block transfer. Okay, for entire block transfer, it takes the control of the buses. Now CPU will wait until the DMA finish, right? DMA finish. So that's why, see here it is burst, right? Burst means burst amount of data. Burst amount of burst amount of data transfer. Burst amount of data transfer. So that's why here entire block is transferred, right? That's why here entire block is transferred. So now what is the time percentage of time CPU will block? So that will be transfer time to memory, okay, transfer time divided by preparation time plus transfer time, okay, preparation time plus transfer time into 100%. So here it is fast transfer, but CPU will be blocked for longer, right? Why CPU will be blocked for longer? Because whole block have to transfer, right? Entire block have to transfer. Okay, but please take care about this formula, right? Percentage of time CPU will be blocked in case of burst mode. Okay, case of burst mode. Now what is the time in for cycle stealing? Okay, what is the cycle stealing mode? Cycle stealing mode says that it says that DMA controller. So this is DMA controller. Okay, DMA and C stands for controller. It steals once one bus cycle at a time. Okay, so it steals one bus cycle at a time. Okay, it steals one bus cycle at a time. So CPU executes slow down but does not stop. Okay, so here it here it CPU, see here CPU waits less than burst mode. Okay, see here one entire block will be transferred, right? Here entire block will be transferred. Here entire block will be transferred. But here what happens? Here what happened? As soon as one byte is ready, okay, I think as soon as one byte is ready, okay, one byte is transferred. Okay, as soon as one byte is ready, one byte is transferred. So here one cycle, okay, one cycle, the CPU DMA will still, okay, DMA will still. So if you look high level picture, you will found that CPU execution just slow down, okay, just slow down, but it does not stop. Okay, it does not stop. Now this is the percentage of time CPU will block, like transfer time divided by preparation time into 100%. Okay, into 100%. Now the last mode is interleaving mode. Okay, last mode is interleaving mode. So here, see what is the interleaving mode? No CPU waiting or blocking. Okay, no CPU waiting or blocking. Here CPU and DMA controller use different memory modules. Okay, they use different memory modules. So here there is no CPU waiting or blocking. Okay, no CPU waiting or blocking. So it's the best performance it is giving among the DMA modes. Okay, among the DMA modes. Now this is all about the DMA transfer modes. Okay, DMA transfer mode. So I think this is the last slide of short notes. Okay, this is the last slide of short notes. Now the key DMA like key points for the DMA. So DMA is the fastest method for I/O to memory data transfer, right? So we have seen three modes. See, we have seen programmed I/O. We have seen interrupt-driven I/O, and DMA. So out of them, DMA is the fastest method. Okay, this is the fastest method. This is the fastest method for I/O. Okay, this is the fastest method for I/O to memory data transfer. Okay, I/O to memory data transfer. Now here at a time, only one of CPU or DMA controller use the system buses. Yeah, you know this. Like at a time, only CPU can do or DMA, because if DMA have to transfer the data, then it will stall the buses. Right, it will stall the bus. And DMA transfer can occur during the instruction execution. Right, it can occur during the instruction execution as soon as IO comes. Right, IO comes. Now DMA transfer cannot occur during interrupt service routine. Okay, when you are servicing interrupt. Okay, when you are doing interrupt service routing, at that time you can't perform, because if you when you see the operating system, you will find that this particular, when you execute this is the highest level. This has got the highest level. Like no other thing can perform, when this particular thing is executing. Okay, this particular thing is executing. When ISI is executing, when that function is executing, no other thing can perform, got it? And this is the maximum data transfer without the CPU intervention. Okay, without the CPU intervention. Like if you have your, like, see, these have diag pyqs, right? Diag pyqs, like this formula, right? This only formula, diag pyqs. If your data count register have x number of bit, okay, x number of bit, how much data transfer you can do at a time? Okay, in one go, you can transfer, in one go you can transfer 2 power x minus 1. Okay, 2 power x minus 1. So this much you can transfer. Okay, maximum data transfer without intervention. Okay, without intervention. Now, okay, now this is the last point. Okay, this is the last point, like CPU efficiency order. What is this? How the CPU efficient from least to most? Okay, so this is the least efficient, right? This is the least efficient program IO, because you have to poll, you have to keeps on polling, right? Polling, you have to keeps on poll, right? Then interrupt IO is less efficient, like somewhat good efficient, right? Then program IO, because whenever interrupt comes at that time only CPU interrupt comes. Okay, then only then only then only CPU takes care. Okay, CPU take care. And the last important, and the best important, most important, like most efficient will be DMA. Okay, DMA. Got this? Got this? So with that, do you have till now any doubt? Everything is got? Okay. Yeah. Yeah, so we have seen entire DMA things today, like entire things DMA we have seen. We have seen C control unit and entire short notes. With that, entire short notes is over. Right? Different, each and every important necessary formula. Okay, necessary points. Okay, necessary points I have added. Okay, I have put. Okay, and so this is all about the COA short notes. Okay, if you want to take the if you want to see the entire course, you can enroll in the EPT and you can watch my lectures. Okay, so in that I have discussed each and every topic in a very much detail. Okay, very much detail, so you can discuss with that. So with that, entire short notes is over. Okay, with that, entire short notes is over.